What I want to talk about today, of course, is the geothermal project, and it has its time come. And this has been a long journey, and I've got a number of my colleagues listed here that have also been along on the journey with me, hoping that Brian will be able to make it later on tonight, but also Catherine Arbuthnot from Campion College, Dr. Lawrence Vigrass, who's an emeritus geology professor, now retired, and then Janis Stokes from Stokes Consulting, who's also helping out with this project. I also want to recognize we have a geothermal working group on campus of interested people in arts and science and engineer. All of us are trying to pursue more sustainable energy sources on campus. So having said that, I'm going to flip to the next picture. Catherine Arbuthnot and I are running a series of focus groups. And what we're trying to figure out is what impediments there might be to people considering alternative energy sources, and specifically looking at geothermal resources. And so that has informed the outline that I've got up front for you to see today. So we're going to start with, first of all, what is geothermal heat? We're going to talk about geothermal systems, both the natural systems as well as the industrial systems. A little bit about the history of the first University of Regina geothermal project. Then I'm going to talk about some of the potential that we have in this province and the rationale for why we might want to consider this as an alternative energy source. I will be talking finally then about the proposal that a group of us have put together on campus. And you'll notice we put UR, that's our little geothermal demonstration project proposal. And then finally summarize it with what I think are some of the key points that I'd like you to take away with you tonight. I've got two pictures here, and this one I took when I was in Iceland. And what I would like you to notice is you can see the steam that's coming up from the ground. We all think about Iceland often when we think about geothermal processes and using geothermal heat, and they're actually using it. There was some, they were using it to heat this complex here. We never did find out what it was, but there is a contrast of Iceland, and then of course here we have our beautiful prairies. So why would we think we can do geothermal in the prairie? So that's the journey I'm going to take you on. So, first of all, what is geothermal heat? Well, geothermal heat actually is the natural heat gradient of our planet. And so if we took a journey from the crust, I'm used to having a pointer there, so if we took a journey from the crust, and as we move towards the center of the Earth, it gets hotter and hotter and hotter. The graph to the side here shows us we start at 0 degrees Celsius and we go to, or 0 degrees Kelvin, down to 5,000 degrees Kelvin. And then, of course, if we start from the center or we start from the crust, we notice that as we go down through the crust, through the mantle, through the outer core, through the inner core, and get to the very center of our planet, by that time it's about 5,000 degrees Kelvin, which is incredibly hot. So the geothermal gradient then is a natural gradient. The source of it is from the Big Bang. From the original formation of the Earth, we're still getting residual heat from that, and also from the decay of radioactive elements such as uranium and thorium and potassium that we have in abundance in the crust as well as in the mantle. And of course, this radioactivity releases this heat energy that we can feel going up through the crust, ultimately getting to the surface. Globally, if we look at the global geothermal gradient, it's roughly 25 to 35 degrees Celsius per kilometer. So what that means is that for every kilometer that we would dig down into the Earth, it would go up 25 degrees or 30 degrees. Go down another 2 kilometers, then you're getting close to maybe 50 to 60 degrees. And that's the geothermal, a natural gradient that we have. So what happens with this heat, of course, the important part of our story, is that as the heat is coming up, it's heating the rocks. And as it heats the rocks, it's also heating whatever else might be in the rocks, such as water. And ultimately, this water then can be heated, and we have hot water at depth. And sometimes, of course, we see the water coming right out to the surface when we have some of the geothermal springs or even the geysers are evidence of heating of water by these natural sources. So when we look at these natural systems, we can identify really two sort of natural systems that we can identify that we might be able to utilize for our own purposes for geothermal energy and heating. And the first one are the magmatic type. So this is related to magma. So magma is molten rock. And it relates to the fact that we can have rocks that are heated up, and they can start, because they're hot, they can start working their way up towards the surface. And we know all about this because sometimes we see that. Sometimes the magma makes it all the way to the surface. So this is Kilauea on Big Island in Hawaii. So we know there's volcanoes there. We know it's hot. There's a very high heat gradient in that area. But in other places, the magma might not rise right to the surface, but nevertheless, the fact that we have this magma coming up towards the surface, it can increase the heat. And of course, that heat then can end up traveling up through the crust out to the surface of the earth. And I'm just showing, here's a magmatic intrusion, molten rock, and of course, it didn't quite get to the surface in a volcano eruption, but nevertheless, it did heat things considerably. Typically, if you've got very shallow magma intrusions, or the intrusions are less than 2 million years of age, typically they can generate very, very, very high heat gradients. Now remember I said sort of a typical heat gradient is 25 to 30 degrees Celsius per kilometer. Now we're talking about 100 degrees to 600 degrees Celsius per kilometer. So very, very hot, and certainly can heat up not only the rocks, but any water that might be in the rocks as well. And we can use these high temperatures to heat water, to heat air, and if it's hot enough, we can even use it to drive turbines to create power. And of course, Iceland is a wonderful prime example of an environment where the magma is very close to the surface. They do have eruptions, and so very high heat gradient in that area that they can utilize, and certainly have. So I'm just showing you that a lot of the sort of immediately obvious places to try geothermal is often where there are these plate boundaries. So the outer crust of the earth is actually made up of a whole series of interlocking plates that actually slowly are moving. But it's where these plates come together. Here's the North American plate. Here's the Pacific plate. And we have this boundary all along here. And you've all heard about San Francisco, where the plate's sliding past. In other places, plates are diving down underneath each other. But these are areas where you get very high heat gradients. So they're natural areas, again, that you would think first off for geothermal energy. Another location, of course, I'm going to show Iceland again. Hello, Brian. So here are some of the geothermal geysers that are in Iceland. And Iceland, too, is located along this plate margin. And so, again, it's a very high heat flux. So, again, you can heat water, and the temperatures are high enough you can generate power. So that's where a lot of them, and all of these little black dots you see here are all geothermal fields, and you'll notice that a lot of these geothermal fields are associated with these plate margins. So that takes us to our next system, because we don't have any modern plate margins in Saskatchewan, but what we have is sedimentary basins. So on this map of the world, you'll see all these green areas. And these are all onshore sedimentary basins. So all of these areas, Latin America, throughout Africa, large areas of China and Russia, all of these areas at one point in time were old inland seas or ocean bottoms. So these ocean bottoms then are just like our oceans today. And if you go along the side, this blue color is showing offshore shelves and basins that are forming right now. So we have erosion from our continents, and all of that sediment is going out into the oceans. And in these ancient basins, it was the same thing. We had the Western Interior Basin, which extended basically from the Arctic Ocean all the way down to the Gulf of Mexico, and this was a huge inland sea. And this huge inland sea, again, there was erosion from the land, and materials got washed in by rivers and streams and got deposited And so we've got layers of sand, and we've got layers of silt and clay. We've got, if we were near the equator, we might have some coral reefs, some limestones that got formed. So these sedimentary basins then are like these layer cakes of layers. And the geothermal gradient in these basins is a little bit more modest. It's maybe about 30 degrees Celsius per kilometer. But we have this layer cake arrangement. And what's really important about the layer cake arrangement is that some of these beds are very, very porous, like some of these sand deposits. You've all been to sand dunes and you know how it's easy to sort of fluff the sand. Well, there's lots of spaces in between the sand grains. And so in these units where we have the sands, that's where water can be stored. That's also where we find oil. It's also where we can find some gases in these traps. So again, I'm trying to show you a basin here, a sedimentary basin. And these sedimentary basins is basically what Saskatchewan is made of. The southern part of Saskatchewan is the Williston Basin, or the Western Sedimentary Basin. And it is a source of great riches for this province. Not only do we get oil and gas from it, but we also have gotten coal from it for power generation. And we also have lots of water that accumulates within this same basin. And it's this water that we want to utilize and use to produce heat for us. The other thing I wanted to mention is that the basin is also the reason why we have such a rich resources of potash in the province. So this sedimentary basin has really been a blessing for Saskatchewan in so many different ways. But what happens is that in these basins you have water that can get trapped in those sands. It's 2 kilometers down. We talked about that geothermal gradient. So the water can be heated up to 60 degrees, even 100 degrees in some cases, or hotter. And it's this very hot water that at very high volumes in these very large sedimentary units that we can utilize and use to, for geothermal energy and heating. So here you can see these sedimentary beds. Oh, I'm going to go back. And you can see that in this particular example, there's lots of water there that we can use. Now, we can use water when it's at very high temperatures. We can use it, in this example, we can use it to drive turbines to generate power, and that's what they're doing down at deep, which I'll explain a little bit later. But in other areas, the water might not be quite as hot, and so we can use it in what's called direct use applications. In other words, we don't want to use it to generate electricity. We're going to use it to directly heat our homes or heat water or heat air. We can use it directly without having to go through changing it into electricity. So it's called direct use applications, and it's primarily used in what they call district heating of water and air. And that's the example here where they pulled the water up and it's running through tubes, and it's basically radiant heating. So when we look at geothermal potential in all of Saskatchewan, in this plot that was made up actually by a fellow by the name of Steve Grasby. So back in 2006, he put this together. And all of these pale blue areas that you see here, all of these are sedimentary basins. So we have, here's Hudson Bay, a sedimentary basin, southwestern Ontario, out here in the Maritimes. So all of these sedimentary basins might potentially have very porous beds with water in them that might be hot enough that we can utilize. So when Steve put this together, at that point in time, 2006, he had data from the Spring Hill mine. They're using heated water in a mine, in this case, for some heating applications in the town. There was some data at Meager Creek, but these are, it hasn't been super active in the last 200 years. I think was the last time there was an eruption in this particular area. So it's very hot temperatures at Meager Creek and Pebble Creek. But look out here in the middle of the prairies, there is the Regina test hole. And this was the data that he had in 2006 to tell him about the potential of geothermal and sedimentary basins and geothermal potential across Canada. And there we are, southern Saskatchewan. We're already on the map. And I go to conferences all over the world, and it's amazing. We see this Regina test hole, the data on the map. So we're there. So I'm going to go from these natural systems now to some of these industrial systems and how we can utilize it. And I'm only going to mention a few things. It's one of the things that since Brian's the one that dragged me into this in the first place, is that the innovation that's going on right now is unbelievable. So the first thing I'm going to talk about is the geothermal heat pump. And in this case, this is the geothermal heating that a lot of you have probably met someone that said, oh, I know Fred down the road, he's put geothermal heating in, or I know someone's done this. Anyone who says they've got geothermal heating, this is probably, well, I would say this is what they're talking about. So strictly speaking, it's for the purists, it's not real geothermal heating because it's not being heated just by the geothermal gradient that I talked to you about. But it's just as effective, and we do call it our own, so it's geothermal heat pumps. And the way it works is it works with seasonal temperature differences. So in the summer, it's very hot outside, and air can be taken from the buildings. It can go down into a series of pipes, or you can put water through as well. A series of pipes anywhere from 150 to 400 feet. And so the soil or the ground feels much cooler than the air in the summer. And so when this hot air comes down through the system, it gets cooled, and then it's this cool air that goes back in and cools the building. Conversely, in the wintertime, when we've got very cold winter temperatures, again, that cold air or water can be taken down, and now the ground is warmer than the atmosphere, and so that air is warmed, and then it's pumped back into the building. So they're relying on seasonal variations in temperature. It's the solar radiation that's driving this sort of geothermal system. And this geothermal system is really taking off. I was down at a conference in January in Waterloo, Ontario, and they told me to go to the hub, take a look at the hub. So I've taken some pictures here for you. This is, there are 8 of these towers in the hub. It's accommodation, and then down below they have a commercial buildings. They've got some restaurants and stores and whatnot down here. But this entire complex is heated by these shallow geothermal heat pumps, the entire complex. And not only are they heating the water and the air in this complex, but they've also put pipes underneath some of these areas. This is what they call their promenade. And there had been quite a big snowfall a couple of days earlier. You'll notice that in this area the snow's fairly deep, and on all the flower boxes here there's still snow, but out here there's no snow. And that's because they put pipes underneath that are warming the concrete in the promenade area, melting the snow. They have drains that drain the water away, and this is kept snow-free. It's really cool. And I talked to a number of the people there that work there, and they're thrilled with it. They're thrilled with the heating and cooling, and they really like the fact they don't have to go out and shovel anymore because it melts away. And the other thing that the one lady said to me, oh, she says, I don't have to do nearly as much cleaning because, of course, it's dry when they come in. They don't have sort of mud and water all over their winter boots when they come in. And so they're very enthusiastic about this system, which we could do here in Regina. We could build a system like this. So that's one type of industrial system. The second type is the deep geothermal energy. And that's where the water is really heated by that geothermal gradient. And so the heated rocks that we talked about earlier, we've got the gradient very hot, it's heating the rocks and heating the water that's in it. And of course this water can be drawn up through, it can go through, it can turn turbines, they can draw up steam, turbines can go through the turbines and then ultimately produce electricity. And this is what they're doing in Iceland for some of their systems. This was a hydroelectric plant that we went through. You can see all the steam coming from it. But again, that's what they're doing. They're taking this very hot water, or steam, and it's hot enough to drive turbines, and they're producing electricity. And this is sort of one of the turbines inside the building in Iceland. Now we're trying to do the same thing here in Saskatchewan. There's a company, private company called the Deep Corporation. I don't know if you've heard too much about this, but they are developing the first geothermal power facility in Canada. And so what Deep has done, they've drilled 2 wells so far. I think the last well is one of the deepest wells that's ever been drilled in Saskatchewan. I think it's close to 4 kilometers, about 3.8 kilometers. They're drilled it down to the Deadwood aquifer, which I'll be introducing you to shortly. And they're harnessing waters that are in excess of 110 degrees Celsius. And they're going to be using this water, bringing it up, and again using it to create long-term renewable baseload power supply. And this is all occurring down near Estevan, near Torquay, am I pronouncing it right? Torquay. So they plan to have 5 of these 20 megawatt power plants. Each one of them can power 5,000 to 20,000 households. So it's really quite an amazing project, and it'll be several years obviously before it's completed. This is really high tech. But I wanted to show you, here it is out here in the prairies. This is for drilling their first well, and of course this is another shot of it. One thing I wanted to point out to you is that geothermal systems, industrial systems, don't take a lot of space. They're not like the great big sort of hydroelectric plants that take up all, that drown all the land. They're not like the big nuclear plants. These don't take up much space. So they're very efficient that way. I just wanted to put this on to show you all the countries around the globe that are currently have geothermal power systems already working and operational. So the red ones are the countries that have greater than 500 megawatts installed. So certainly the US is way ahead. Certainly Italy, Kenya, the Philippines, New Zealand. Then there's a group in the middle that are 100 to 500 megawatts installed, some of the Central American countries and Turkey. Then there's a group that they're just getting into it, less than 100 megawatts installed. So that's looking at sort of France and Portugal and China and Russia. And this was based on the most recent, this is 2015, it's advanced since then. Notice that we have nothing in Canada. But with Deep, we're going to be able to color this eventually too, that we've also got involved in this electrical production through geothermal. So the second type of geothermal that I want to talk to is also deep geothermal, but in this case, the temperatures are not as high. So they're not as high to be able to create steam and drive turbines. So in this case, this is that direct use that I had mentioned earlier. So in this case, again, we would be extracting hot water from somewhere underground, deep underground, couple of kilometers down. That hot water then is taken up into a building, a heat exchanger, and then the heat is through the heat exchangers transferred to surface water, and then that hot water is sent around to various buildings or factories or whatever your application is for this direct use geothermal heating. So I've got 2 examples here for you, and this is what we're proposing for the University of Regina. But we have 2 examples. This one is then The Hague, and in 2010 they put a system together which would provide heating for 4,000 new and existing homes and 20,000 square feet of office space. And then in France, at the time of this, they had over 61 geothermal district heating projects since 1969. And from that, it provides heating for over 200,000 residential units, and they're saving about 650,000 tons of CO2 emissions each year that they are avoiding by using this rather than gasoline. So that's a significant reduction in terms of CO2 by using this system to heat these buildings and heat this water. And this is an example of one of the doublet systems in Paris. So I'm going to switch now that I've told you about these various systems. I'm going to talk now a little bit about the first University of Regina geothermal test well. And this was drilled back in 1978, 1979. And the objectives of this was to demonstrate that sedimentary basin geothermal energy was, could be done in Canada. So that was one of their objectives, to prove it would work. And the second one was to supply air and water to a new sports complex. So one of the people that was really promoting this whole system was the former president of the University of Regina, Dr. Lloyd Barber, who was a really great proponent, really championed this project, but he wanted it to build a new sports complex, which of course never got done. It was promoted by the president, by people on campus, and it was funded largely from the federal government, NRCan, Energy and Mines, and then also from the government of Saskatchewan. So the pictures I have here are actually courtesy of Dr. Vigrass, who was one of the people involved in this project. And so here you can see 1979, here's the oil, or the well, that's been set up on the University of Regina campus. So they were drilling, and this is showing a cold day in January. And you can see the guys here are drilling the hole for this first geothermal well back in 1979. So they drilled one exploratory well. The well was drilled down to about 2,226 meters. It was cased all the way down, but at the bottom, about the last almost 200 meters, it was left open so that water from the aquifer could get into the well and be drawn up by pumps. Unfortunately, to complete the system, they needed another well. So you need one well to draw the water up, and then you need another well to be able to put it back down into the aquifer. The second well was never completed, and so the project was not completed. And Dr. Barber did not get his athletic facility as he had wanted to. And in 1999, they actually capped the well. Now, why did it stop? Well, I've got lots of these graphs that are showing some of the reasons for this, sort of the ups and downs of our fossil fuels. But certainly it coincided with a drop in fossil fuel prices. So it was cheaper to use gas, they felt, than to continue on with this project. There was a change in government who had a different mandate. And then there also was increased availability, and also I think renewed optimism after the 70s. I remember the fuel crises of the 70s when everybody started buying smaller cars. All of a sudden, you know, there seemed to be lots of fuel, the prices were low, people started buying big cars again. And again, I think the whole thoughts about looking at alternatives sort of evaporated. So it was never completed, and I wanted to put this picture in to show you. This is 1979, and this is the Regina campus. And here you can see the physical plant in 1979, and this is the main plant where water is heated and cooling and air is heated as well and distributed around the campus. And here it is in 2018, and I'm trying to take the very same view. And you can see now that we have parking lots in here, a lot more buildings than we used to have. The facilities, the physical plant is still there. And, but I looked all over, I could not find where that old hole was drilled. I couldn't find it. So again, just to reiterate, it's a very small physical footprint that geothermal systems actually have. So what did they find out from that very first well? Well, they found out, they drilled down to the Ordovician Cambrian, right down above the Precambrian basement. Precambrian basement underlies the entire province. It's that kind of purpley brown color there. And just over top of that is something they call a basoclastic unit. And it's in this unit that they found they have what they're calling the Deadwood Winnipeg aquifer. And they discovered that there's about 111 net meters of effective sandstone. And this sandstone is very porous, and it was containing all of this water that had been held for a long period of time, so it was very hot. And They discovered the sandstone has a porosity of about 13.2%. Again, permeability 350 millidarcies. I put that in mainly to show you that this sandstone is very porous. The water can flow through and move, and it was a really great reservoir for this water to sit for a long period of time and heat up. And I've just got another arrow here. Here's our basoclastic unit, and then this is the basoclastic unit. And remember when I said it was a geothermal basin? That we had the sedimentary basin. You can sort of see that basin shape because all those sedimentary packages are actually thinner towards the north of the province. So this is the Precambrian shield. And then as you head south, that basal unit, that aquifer gets deeper and deeper. So that by the time you're down here at the US border, this aquifer now is about 4 kilometers from the surface. So in the Regina well, what they discovered was at the base of the well, temperature of that water was about 61 degrees Celsius. And here's a plot sort of showing that as you go down again, that typical geothermal gradient, the temperatures are getting hotter as you go down, and the water itself was about 61 degrees Celsius. And they calculated that if they pumped this water up at a rate of about 110 cubic meters per hour, that by the time the water got to the surface, and this is 2.2 kilometers from the surface, by the time it got to the surface, it would have cooled down only a couple of degrees. It would still be 59 degrees Celsius, which means it would still be quite viable to use for geothermal heating. Now, this water is not your typical water. It's actually a brine. So it's full of all these dissolved solids. It's full of the sodium chloride and sulfate brine. And actually the dissolved solids are about 108,000 grams per cubic meter. So it's, again, you wouldn't want to drink this. Not very nice. But of course the concern is always about corrosion. So they ran some limited corrosion tests and found that there was relatively low corrosion rates as long as they kept the water away from any oxygen, so they wouldn't have oxidation. And so the system that was designed is basically a closed couplet system, again trying to isolate that brine so that it doesn't come into contact with any air. So from this project, there were over 40 research papers and technical documents that came from this one single well. And it was all reported just lying underneath the current University of Regina campus. And Dr. Lawrence Vigrass headed up the energy research unit and was really the main researcher that coordinated all of these projects that went on from this one well that was drilled. If we look at the timeline it takes to develop some of these different energy resources, we can look at something Catherine Hickson put together, and it's sort of looking at how long for the exploration to the actual development of the facility. And first of all, she said you need to identify your location where you think that this might be a good place to put in a geothermal system. Then you have to do your surveys and check out all the data. Again, you've got to try to convince somebody to drill so you can actually test the well. And then once you've done that, then you're at the point, if it looks like it's a go with all of the measurements you've taken, then it's the decision to build. So where is our project now? Well, after 1979, we're still here at the decision to build, because they certainly demonstrated that on campus this would be a viable system for heating. So most of the risk, of course, is in the exploration, and it's when you put the well down to see if you've got the resource you need. And so all of that has been taken. Most of the risk is gone. So there is widespread geothermal application, not only underneath the University of Regina, but throughout a good portion of the prairies. And certainly this turquoise blue is showing where you've got warm water potential for direct use heating. And then of course, as you get deeper and deeper to that aquifer down by the US border, that's the zone where you get temperatures that are hot enough that could generate electricity. So we do have the resources in Saskatchewan to develop a geothermal industry. And if we look at it a little bit more closely, I just love looking out of the prairies when I'm flying along. It's just, every season, it's just so beautiful. At any rate, this is in the fall, obviously. But they measured the temperature at the base of that aquifer. And so this map that I'm showing you here, all these lines are joining areas of equal temperature. So if we draw this line along the 50 degrees Celsius, we'll notice that using that as our cutoff, that there are many, many communities that are below this 50 degree cutoff, which is about 51.5 degrees north latitude. Here's Saskatoon up here, and there's Yorkton, Regina, Moose Jaw, and so on. Many communities that actually could utilize this resource. And there's a number of hot spots. I'm just showing Regina and Moose Jaw. Regina is about 60 degrees at the aquifer. Moose Jaw is closer to 70. Swift Current is 70. And then, of course, down here in Estevan, they estimated it around 110 degrees Celsius. So many areas that we can use this sort of low-grade geothermal temperatures. So I found this plot because it shows, I've just told you that most of the temperatures in Saskatchewan are more of this sort of low temperature grade, less than 90 degrees. We do have some that are more moderate temperatures, and that's where deep comes in for producing electrical power. But even within these low temperatures, I've sort of tried to outline all the different applications that one can use using geothermal heating, direct heating. So everything from snow melting to fish farming, swimming pool heating, space heating in your home, greenhouses, space cooling, food drying, all of this could be done using the temperatures that we have here in Saskatchewan. And if you're thinking of it, I just put a couple more in here just again to show you some of the applications that can be used. They're very thrifty in Iceland. Nothing is wasted. And so after they put the water through to develop the electricity, they run it through and heat air and water. But then the water that's left over before it's pumped to wherever it's being pumped to, they were doing some road construction. And you'll notice all of these hoses that seem to be here, all coiled under the road. And they actually run their the water from the aquifer under their roads. And yes, here it is in winter in Reykjavik, and wherever they have it all heated, of course, that keeps snow free, and then these areas, of course, have snow. And so again, talking to people there, they don't have to use salt on their main roads. They don't have to have as many trucks clearing off the snow. They have fewer accidents of people slipping and falling again because they're melting and removing this snow. We could do the same thing in Saskatchewan. We could do the same thing in Regina. The other application that I think is really, really neat is this, and this is, Brian Brunskill took this picture over in the Netherlands. In the Netherlands, this is an 18-acre greenhouse complex. They have their own geothermal plant that's heating the air in these greenhouses. And what gets me excited about this is that, did you know that southern Saskatchewan is the solar capital of Canada? We get more incoming solar radiation than they do in Rome and Rio de Janeiro. So here we are in this wonderfully rich province. We have all this solar energy so that we could have greenhouses. We'd have geothermal to heat it. We've got our transportation hub. We're in the center of North America, and we could grow our fruits and vegetables in these greenhouses and ship them all over. And I was reading about, there's a group, the Ivor group, Rocky Mountain House in Alberta, and they started drilling this summer, and that's what they're doing. They're building greenhouses in Rocky Mountain House, and they're going to heat it by geothermal heating. And so I think we could do that too. So another picture again, just to remind ourselves of all the different things that this geothermal heating and water can do. Again, we can even get into biogas production, which is another whole story. obviously snow melting, bathing, heating buildings and water, mushroom culture, and one funny thing, apparently down in the States, they've got a lot of these systems that they're starting to develop as well, but one of them, Catherine said that it's an alligator farm. Apparently, they're using geothermal heating for these alligators, which I was very intrigued about. So when we start looking at our energy use, and I'm going to start by looking at Iceland. So how are they utilizing their geothermal? Well, obviously they've got temperatures that are hot enough for electrical generation, but they're also using 40% for electricity production, but also 43% heating space, heating buildings, 2% for greenhouses, 5% for fish farming, 2% industry, 4% for snow melting. They have a very nice road network there. And of course, 4% for swimming pools. When we look at Canada, what is our use of energy? And I got these from NRCan Fact Book. When we take a look first at our commercial and institutional use, most of the use that we have for energy is in space heating and water heating. So we've got about 63% in commercial institutional is used in heating. If we look at our residential dwellings, in that case, we've got about 81% is used for space heating and water heating. That's our real need, is for heating. So I guess my question is, why don't we add direct use geothermal energy into our energy mix? Why are we using electricity to get our furnaces to work when we can just pull the water up and not have to make it into electricity but use it directly for heating water and our buildings? And we could do this in some places. I showed this plot just to show you what's going on in Europe. So all the red areas are showing areas where they're using sort of direct heating and sort of geothermal resources in Europe. And the interesting thing is that direct use geothermal technology has been around for a long time. They've been using it for over 45 years in Europe. And this district heating is used to heat buildings, to heat homes, to heat industries. It's used for commercial buildings. It's used for aquaculture, greenhouses that I showed you in Holland, Netherlands. In fact, the Netherlands reported that their geothermal use was up 19.5% in 2018 alone. And if we take a look at this, these are the number of geothermal direct heating facilities throughout Europe. And notice that France and Germany have over 90 of these facilities throughout their countries. So they're already using them, and they work very effectively. So when we think about the state of the technology is not new. We can complete a geothermal installation by integrating a lot of the expertise we already have in the province. We have all the experts that have been drilling oil wells and gas wells and directional drilling. All that expertise is here in the province that could be used for geothermal. We also have people, engineers, of course, involved in infrastructure heating that are well aware of how to hook things up for radiant heating. So we have the expertise right here in the province that we could do this. The other wonderful thing about this geothermal is that it's not restricted by any intellectual property. And most materials we could already get just off the shelf. Wouldn't need to be special builds. It's already available. And as I said, the technology is being used throughout Europe and many other areas now for heating. So here we have this wonderful big province of ours. And then I just wanted to show you this. This is Munich. And I don't know. Oh yeah, you can see them. You can see these little sort of orange diamonds here. These are all geothermal wells that they're using for direct use heating and other applications. And there's 17 of them just around Munich alone. So in 2015, our research group presented a proposal to the University of Regina to construct a deep geothermal demonstration project at the university using heat from the Deadwood aquifer. And this proposal would complete what was started in 1979 using their data and the experience that they gained from that. We suggested a small-scale demonstration model. It would be like a legacy project. It will certainly will outlast me and certainly many generations of students once set up. It would provide base load heating for the university. And as well, if you did locate on the university, it would be a site for research and innovation, training of highly qualified personnel, and people in the geothermal industry. So Saskatchewan would be one of the first provinces to use direct use geothermal aquifer district heating in Canada. But other places are catching up. So what we proposed to them, and this is the block diagram, so this is showing the aquifer, the Deadwood aquifer, down 2.2 kilometers. And we proposed a geothermal doublet system. And the way this works is that we would drill 2 holes, about 2,200 meters into down to the Deadwood aquifer. They would be drilled directionally. So they would be about 5 meters apart at the surface, the drill heads, the well heads. And then they'd be about 1,300 meters apart at depth. And we would locate them out here to the facilities, the physical plant. And I'm just going to show you. And this is right underneath the campus. So this hot water then, we would draw up from the Deadwood to the surface. That hot water then would be taken through a heat exchanger. And then the heat would be transferred to city water that we would run through, and that city water then, or surface water, would be heated. And then once the heat was taken from the brine that we had brought up, then that would be sent back down, back down to the injection well. So it goes up, it's a closed loop. The brine never gets mixed with any surface water. We would simply be heating surface water using the heat from the brine, and the brine would go right back down into, by the re-injection well, right back down to the aquifer. And we figured that we could place these, drill the well right outside of the physical plant, and it would be right on campus. And I'm going to show you in a second here just where that physical plant is. But once that water was heated up here, through that heat exchanger, it would then be, using a district heating system, would be sent around to the various buildings for heating. Now, the buildings that can be used for this kind of heating use radiant heating. And so one building that is capable of doing radiant heating is the new Kisik Towers that has been built, and they're using radiant heating. So with this system, the calculations we made is that this doublet system could provide heating for over 1.2 million square feet of residential space. Or if we put it another way, it would be about 500, 1,400 square foot homes that this system could heat, which is, I think, pretty neat. And it would do it for over 60 years that this well would last. The energy is sustainable, it's reliable, and it's green. So we suggested tying it into the existing infrastructure, the heat grid that they have. We could use existing space that's already in the physical plant. There's room right there. We wouldn't have to build a new building for it. And so this would augment the physical plant. It could heat this Kisik Towers, and it would only use 60% of what the capacity would be, because Kisik Towers is about 300,000 square feet. And again, it's a geothermal ready building. You're already using radiant heating, and so you would be able to hook this up to it fairly easily, I would think. What we were suggesting is that we could drill, there's a parking lot, we could have the drills and the well holes right outside of the physical plant. And again, as you saw with the other one, it really does not take a lot of space. Once you have the wells, and they would be 5 meters apart, then of course you would be right beside the physical plant, and that would go through the heat exchanger there. So we would have excess. We'd only be using 60% of the capacity. The excess could be used to heat the domestic water on campus or for Pasqua and Wapka Towers. We could heat the university pool, And again, because this is very hot water coming up, it would also provide combustion preheating within the physical plant itself. They wouldn't have to heat up anything ahead of time. It would be heated by these geothermal waters. And of course, any future builds could be built with radiant heating. So we believe that using this deep geothermal energy will contribute significantly to developing new energy sources and reducing our environmental footprint. And again, as I said, I like taking pictures out of the airplane. So here's our beautiful University of Regina campus. Here's that physical plant that I showed you. So putting in this system, we believe, will be a source of innovation, sustainable energy development, as well as green infrastructure. So I'm just going to go through each one of these really, really quickly just to talk some of the benefits that we see would be coming to the University of Regina. So in terms of innovation, and I had to put this one in, this is the Innovation Indicators Report Card. And I must admit, if my kid came home with something like this, I wouldn't be too happy with all the Ds. I think Saskatchewan, we've got lots of brain power here. We can be innovative. We can do lots of innovations. So I think that by building this geothermal plant, we could host Canada's first, again, district heating system. It certainly would be a demonstration that this could be done in a sedimentary basin. We don't need to have volcanoes like they have in Iceland. We can do it here. It would be new green infrastructure. It would be applied industrial level technological innovation, and we could also do it at a commercial scale. We'd learn how to integrate these different energy sources, the geothermal energy sources, into existing energy distribution units. And of course, there'd be so many spin-offs that that are yet unseen. And as I said, there's breakthroughs all the time. People working on geothermal, some really spectacular projects in Europe right now. We also think that this would complement DEEP. If they need any experimentation or anything that needs to be done, because that project to develop power it's a mammoth undertaking. It's a multi-million dollar project. Ours is a very simple project. It's a pump bringing hot water up from depth and circulating it around on the surface. So along with that, we would be certainly promoting and training highly qualified people, which would be jobs in the geothermal industry. And the really important thing about sustainability is the fact that this source would be available for several generations. It will last a long time. Over 60 years is what we're estimating. And of course, doing this would help us develop best practices for geothermal use. Green infrastructure, I wanted to just show you a few graphs because I'm sure that you've seen many of these sorts of graphs. This is showing the renewable energy capacity. So the capacity factor is the percentage of time that a facility is operating at its rated capacity. So when you look here we have geothermal, biomass, hydropower, concentrated solar power, wind, wave, tidal, photovoltaic cells. I mean, you have, sometimes the wind dies down, you have seasonal variations with solar, but the highest one, and very consistent, very reliable, is geothermal, 86 to 95% of the time. So it is, as long as your pump's working, it's working. Because this heat from the center of the earth, our Mother Earth, is consistent. The other thing about, of course, the green and greening of our province relates back to energy emissions. So if we were to utilize more of these, geothermal does not have, it's a near zero greenhouse gas emissions. So we would be eliminating our carbon-based use, or at least reducing our carbon-based use into something that's not going to be putting out more greenhouse gas emissions. So I just put a few things here showing the different types of greenhouse gases that come from the burning of coal and oil and natural gas, and here we are, geothermal. And I put this one in as well, because This is, and I'm sure you've seen this one before, this is looking at the greenhouse gas emissions per capita that they've calculated. And Saskatchewan is leading in that, and there are reasons for that. We do have a very cold province. But instead of just sort of trying to make excuses for why it's so high, why don't we work to get it lower? Why don't we reduce our greenhouse gas emissions? So Brian did some fancy calculations here and figured out that some of the value of using geothermal is that we would reduce the emissions of CO2. And he calculated that if we used a total lifetime of about 60 years, we would avoid about 4,770 tons per year. So over a lifetime of 60 years, that would be about 286,000, 100,000 tons that we would be eliminating from our atmosphere and not putting it in. He also, we thought, what if we had completed that geothermal well back in 1979? And we went back and figured that's 40 years ago. So we assumed that if we had that geothermal well operating for 40 years, and we're going to do it for a 60% capacity, so we're being very conservative here. We've got about 212 days per year when it's heating that it would be working, sort of a full capacity or 60% capacity. We calculated that the heat provided would replace about 52,800 gigajoules per year, or over 40 years, 2.1 gigajoules of natural gas that we would not be burning or would not have burned over those 4 years or those 40 years. And so if we use an average delivered gas price of $4.50 per gigajoule, the gross saving would have been about $9.5 million that we would have saved in terms of using gas. The avoided production of CO2 would roughly be about 2,660 tons per year, or about 106,300 tons over 40 years. So again, that's a lot of emissions that we would have not put into the atmosphere just from this one small system, district heating. And of course, the anticipated lifetime of a geothermal source at this particular pumping rate that I gave you earlier would be about 66 years. And of course, as technology improves, it might be even longer. So we still have another 26 years to go on that geothermal system. And there are very few infrastructure projects that even last 60 years now. So what ifs? I did find this, and what I want you to take away from this, again, you get all sorts of these plots comparing geothermal, fossil fuels, biomass, comparing all of these different ones. I think that what we need to do is start making more choices and deciding what is the best energy source for a particular spot rather than one size fits all. So what I want you to take away is the summarized advantages and disadvantages of geothermal. And what they said was that it's highly energy efficient. Of course, the geothermal heat pump I talked to is one of the most efficient heating and cooling systems. This system is reliable. It's not subjected to fluctuations like wind changes or the sun going down. It's environmentally friendly. It's very low carbon emissions, renewable, sustainable, has a very small land footprint, as I showed you. It doesn't have to be location specific. We now know that we can do it in many areas in southern Saskatchewan. Relatively price stability once it's built, can be very versatile, and it can be used to provide base load or peak power when you need it. It's there. The disadvantages, of course, always back to this, is the high construction costs for drilling. But again, if you amortize that over 66 years, it really isn't very much when you compare some of the other costs of some of these big electrical installations that we're putting up. So in summary, obviously I'm an advocate. I'm very excited about the possibility of even just trying this, doing something new, being innovative, being first in Canada. I think geothermal energy can be a source of reliable baseload heating, and it's available on demand. It has no storage requirements, no direct emission of greenhouse gases, and it will certainly reduce our environmental footprint. We can integrate this system with our existing heating infrastructure, and at the University of Regina, it could be immediately operational. And again, it would showcase clean, green energy technology and infrastructure. Of course, if it's done at the university, it will be helpful in terms of education and research, which will build capacity in geothermal and hopefully lead to employment of highly qualified people that could go elsewhere in Canada and build these sorts of systems. And of course, the building of this one small project, I think, has very far-reaching implications. I think it's more than just what would be happening at the university. I think it would provide a really significant opportunity for community involvement and start the discussion. What are we going to do about our future energy needs? So I'm going to finish with this. On October 29, 2018, and I know some of you were there, the City of Regina unanimously approved a motion for the city to use 100% renewable energy by 2050. Has the time come to complete the University of Regina geothermal project of 1979? So that's the question I'm leaving you with. And I'd like to thank all of my working group who have contributed to this project. And I would be very happy to entertain any questions and try to answer them if I can. Thank you very much. Yes?
Are you presenting at the conference, the Reimagine conference?
I'm hoping, well, I would like to. I haven't been told that I was going to be. I think they're going to be having Kirsten Marcia from DEEP that will be talking at it. But I would love to have the opportunity to talk about this because it is a different form. So Brian, I think Brian is hoping to do something there, but not on geothermal, right?
Oh, that's great.
Yeah. Yes.
Has SR or the provincial government shown any interest in this project, and most of all, any funding?
Well, I mean, that's what we've been working on.
So that you have nothing yet?
Not yet, but again, we've been talking to Innovation Saskatchewan, and we've got some, we've put in for some grants. One of the problems with geothermal relates back to just some of the conditions of lending money, and I know that it is difficult to get money for that. And the other issue that we had was when the government put out a call for innovation, they were looking strictly at the production of power, electricity. And our project doesn't produce power, but it heats. And so we're waiting for another round that we can hopefully get some funding and move on. And I think we're starting to see some movement. Janis Stokes is helping us out now, consultant. And so she's helping us out in that regard to see if we can get some funding and get this thing moving. But it's a very good question. Yeah.
What is the cost to drill both the wells?
The cost for the wells, can you remember just specifically how much, Brian? Was it 5, 6?
The entire project would be about
At 17?
$16 to $18 million.
Yeah, that's the entire project, and including, about $1 million for research as well. But as I recall, when because we've gone through and sort of tried to itemize everything, and the most expensive thing is not drilling the wells, it's actually putting in the infrastructure in the grid to get the pipes to the actual Kisik towers. Between the manpower that it would take to do that, that's where most of the costs were coming in, which was kind of surprising.
Right, how much would it be for the 2 wells?
It's about 5,000-6,000 for the 2 wells. I'm just trying to bring my...
Maybe about between $5 to $6 million to drill them.
Oh, sorry, 5 to 6 million, yeah. 1,000 seemed too low. Yeah, no, 5 to 6 million.
And if you were going to do this throughout much of Regina, is it possible to have enough, or would the heat run up faster because you have more wells into the aquifer?
Well, I mean, it could possibly. I mean, this is one of the reasons why we want to get the demonstration project. We know we can certainly support the demonstration project there, but I suspect we can support more. But again, we need to know more about the rate of water flow, the direction of water flow, the connectivity between the aquifers. So there's a lot more information we still need to get that we could get by doing the demonstration well that would help inform us about how many we could actually place. But that would certainly be something you'd have to consider.
Thank you for your presentation.
Oh, you're very welcome.
You've given me a lot of hope.
Oh, good. Good.
I've got a couple of questions. The first one has to do with, you said it's a 66 year lifespan. Why?
It has to do with something called the flash point. So when you are, and this is some of the things that we would have to calculate by drilling and getting the second well, we could calculate what the flow of water is. But eventually, you know, as you keep drawing water up and putting the cooler water down, eventually you start to cool the system down. And eventually you get to the point where it would cool it down too much. And that's how we're sort of calculating roughly 66 years. But again, with changes in technology, you know, there's always things, but you know, even 66 years, that's a good length of time. But that's a good question, yeah.
My second question is the one I'm always harping on. Line 3 is going from Hardisty, Alberta to Superior, Wisconsin, a few miles south of Regina. When the pipeline breaks, how will the aquifer be affected?
The aquifer is very deep. I mean, the aquifer is 2.2 kilometers down. And the wells, I mean, the pipelines you're talking about are relatively shallow. So I don't think there would be, it would be highly unlikely that it would get contaminated. But even so, this is not water that we would be drinking anyways. And so it's already this very brine rich, but no, the pipelines, it would be, that's near the surface, and this is kilometers below. So
Pipeline 70 feet down.
yeah, so it's, you know, it's not going to be affecting any of that. Yeah.
In Moose Jaw, they have a minerals fall.
Oh, yes.
Yeah. Has there been any study of the potential for building such a system in Moose Jaw?
Oh, they could do that in Moose Jaw. Yeah, because they've got even slightly hotter temperatures than we have. In fact, Brian, you were involved in some of that, I think, weren't you?
In the original spa, yes.
Yeah.
It certainly could be used in Moose Jaw. It would work just fine. Yes, it would work in Moose Jaw just fine.
Yeah.
It would, yeah.
Maybe better.
Yeah, because it's slightly hotter there.
The water's a little warmer.
Yeah, about 70 degrees Celsius. Yeah. So there are lots of applications. I mean, the biggest impediment, of course, is the cost, the initial cost. But even so, I mean, we're looking right now about 18 million to do this. And when you look at the costs of some of the other, you know, some of the big infrastructure we put in that are, you know, hundreds of millions of dollars, it doesn't seem like as much, really. And I think it's becoming more economical all the time.
I'm a professor at the universities. I'm a member of the university community. My question is, what can we as a university community do to support you in your work and make this happen? Because I think it's high time that this happens.
Oh, this is fantastic. Thank you. Yeah, that's great. You know, just coming out to events like this, and you know, I mean, I'm happy to get more people in on the working group and spreading the word. I must say, when we proposed it to PAX, the president's group on sustainability on campus, they were very supportive. They thought it was a great idea. And we did get letters from Vianne Timmins to various agencies and people supporting us as we went out to the government to meet various people. What the impediment seems to be is maybe will and money. And so far, you know, gas prices, as I've discussions with people in the physical plant, they think it's a great idea, but right now gas is so cheap. So we've got to change the mindset somehow for them to think not short term, but to think long term. And so, yeah, I know. I've talked to Neil Paskowitz, and we had one of our focus groups with them, and it was really good because I didn't go in on the focus groups, but got the information back. And so you got a much better feeling for what people are thinking. And, you know, it ends up being the money, the concerns about how much money they're spending, and, you know, the very short, you know, time span that they're looking at, and they're not looking at it over the whole life of this system. So I don't know, maybe you've got some suggestions of what I can do too. I mean,
well, we'll talk later, but
yeah.
I work in facilities.
Yeah.
We've got our budget spent for the
Yeah.
next 5 years.
Yes.
And we don't even touch
Yeah.
a lot of the problems on the campus.
Yeah.
So this
Yeah.
is going to have, you know, this is awesome. Like, I mean, this is a
Yeah. Yeah.
slam dunk as far as,
Yeah.
you know,
Yeah.
you know, doing it, but it's going to require some serious funding from outside of our institution.
Yes, and this is what we've been doing, and this is what we told them. We need support. But the other thing that they're concerned about too is I think that I think they're still not thinking about this as being like a forever heating system. And I think they think it's more complicated than it is. But even within that, you know, that budget, we put in for someone to be hired by the university to run this system, you know, for at least 3 or 4 years. They'd realize that it's not a very complicated system, and we'd be training people to use it. But there's that fear, well, what happens when the researchers go and they don't want to use it anymore? And their comment was, well, we'll just have to turn it off. And we said, no, that's not the point of this. The point of this is that it's a heating system that stays on, and it's there whether people are doing research or not. That's what it's for. So that's another thing that we have to try to encourage them with.
Yeah, it's a cultural change, that's for
Yes.
sure.
Yes. Yeah.
But this, you know, the university's most expensive utility is not gas.
No.
It's not power, it's water.
Yes. Yeah.
So,
Yeah. Yeah.
but you make a really good comment about 60 years.
Yes.
Let's take 60 years and go back and
Yes.
see where we were.
Yeah.
You know, and so 60 years from now, you know,
Yes.
you can't use that excuse.
Yeah.
How old is the heating plant at the university?
It was built in '64.
Sorry.
Yeah.
Another question about a different geography.
Okay.
One of the things you mentioned was the very deep thermal, geothermal that can be used to produce electricity.
Yes.
And you talked about piggybacking on current infrastructure and current knowledge in the province.
Mm-hmm.
And it just strikes me that a lot of research should be done about the Estevan area, because it just happens that they already have the electrical distribution system starting there.
Yes.
They already have the expertise for drilling.
Yes.
And somebody should be doing the kind of study of that potential at the same time you folks are doing the direct geothermal.
That's right. Yes. Yeah. Yeah.
Well, I wanted to ask about what is known about the consequences of this type of terraforming, if there are any, or if there are any hypotheses of what could happen as a result of replacing that hot water underground with cold water. But I also wanted to get back to the comments about the university, and I'm sorry to hear that our budget is set in stone for the next 5 years, because a few of us at the university just worked on getting a lot of climate action put into our new strat plan for the next 5 years. So perhaps we can hold the university accountable to that, to those items in our upcoming strat plan, and maybe push for more aggressive funding, because as I pointed out before, the university has a way of finding funds when it really wants to. Anyways, yeah, is there anything known about any potential for consequences of this type of terraforming, of changing the earth like this?
You mean when you're sort of depleting the temperatures and that? You know, I mean, I think that, I mean, that's, I mean, that geothermal gradient, I mean, that heat is already there. I mean, and it's still coming up. And so I think the consequences would be that, you know, maybe you would get to that flash point and you'd have to stop that particular well, like if you got to that point. But I think in terms of of Mother Earth, if you will, she's going to keep on clicking right along. Because one of the things that we're suggesting, you know, is that we put the water back in. We put this brine back in. One thing that, that Iceland didn't do when they first started doing their geothermal was that they didn't put it back down into the aquifer. And I think there was a perception at that time that there was tons and tons of water. Why would we need to put more in? And that actually, that picture I showed you of the Blue Lagoon, that's all that, a lot of that water that they used that didn't go back down, and that's what's using to heat that particular pool. It's a man-made pool. I had thought it was natural, but it's not. Now, of course, they know, and they're putting the water back down.
Sorry to ask another question. Is the water that you put back down the same water you brought up?
Yes.
Okay.
It's just cooled.
Not cleaning other water sources?
No. No, and this is why we have this closed loop, this doublet system. And that's a good question. I may not have made that clear. We want to isolate that water from oxygen. We don't want it, you know, corroding everything. But that brine water comes up in a closed loop, and it goes through the heat exchanger, so it never comes in contact with any surface water. Doesn't contaminate any surface water. It's just the heat that's being extracted, and then that water goes, the brine water goes back down into the aquifer. So it's this continuous loop. So we're not depleting it, which is another thing that I really like. Yeah, yeah.
Thank you for this.
Yes.
I'm sad it didn't happen in 1979, and it should have happened now. My question is about the placement of the wells.
Yes.
Are you using the first well that was drilled? Is that the placement?
No. Unfortunately, I mean, that's been capped, and in discussions with people that drill, it would be more expensive to try to use the original one and fix it with if there are any problems than it is to just put a brand new one in. And of course, materials are different now too, so we would put in a new well.
Then my question is, my concern, my only concern from this whole talk is about the placement of these two wells right in front of the heating plant. Because it's an award-winning building.
You wouldn't see them. This is it. I mean, once the well was drilled,
they're all underground.
The head is, you could put it completely underground, or there would just be a small thing that would be there.
Okay.
It would not detract at all. You're right, it's an award-winning building. It's beautiful.
Imagine
it's a highlight of it, but no, it would not. It would not be impacting on that. So you don't have to worry. But that's a very good point.
Yes, beauty is important too.
Yes, it absolutely is. It absolutely is. And that's why I tried to show the pictures, that I mean, it's a very small footprint these things have, you know, and we don't even have, no, that was when they drilled it. They had the wellhead, but when they do it, it's just a small thing, and it would be right outside. And that's the other thing too, is we don't have to build new buildings. There's space within the existing physical plant that it would fit right inside. Yeah, which is nice. Yeah.
Question?
Yes.
Can you do, at the beginning you talked about the directional well bores, or the directional wells being 5 meters apart at surface, 1,300 at below surface?
And that's again because you don't want to be putting it right back.
I get that.
Back.
I understand all that, but my question is, can we do multiple, instead of two, do multiple wells, you know, because all the cost is setting up the rig, it's not the actual drilling of the well. They talked about, you know, doing maybe 4 wells and capping them, leaving, as long as the distance under below grade. You know.
Yeah, I mean, at this point, we haven't looked at putting more in. We've just thought about the one system. Oh, sorry. Yeah. But I must admit, I'm also really intrigued. I mean, the city has that area, the rail yards that they've earmarked for something. And that would be a wonderful place to do district heating in there if they were put in, you know, buildings and apartments and stores. I mean, similar to what they've done with the hub would be, I think, really, really nice. Really real showcase for the city.
I imagine that the holes are lined with steel, is that true?
Well, there's different materials that they can use, and they're trying all sorts of different ones. And they were talking basically, but I know they've got some new ones down that they're trying in Europe and stuff, and I'm not sure.
We have the steel plant, which, you know,
yes,
always
of
running
course.
jobs, and this would be a natural. They may be quite excited.
Yeah, that's
if
true.
You're going to stimulate
yes.
The demand for steel pipes.
Mm-hmm. No, you're right. That's a great point. I hadn't thought about that. That's good.
So a lot of this is about on a larger scale, but I've been looking at the idea of an individual like in a house.
No, I don't think you'd want to do it for a house.
Not even like some of the closed loop systems they talk about for
the heat pumps.
Yes.
Yeah, the shallower heat pumps.
Would those still work around here?
Mm-hmm.
Something because I was looking at it at my house and
yes.
we're probably up to about $40,000 to get it installed.
It would be expensive. Yeah. No, it seems to work really well, and the systems I've seen in Ontario, they've been very happy with them. Yeah.
I wonder, just because I'm not knowledgeable about this stuff, the buildings that use, the new buildings that use radiant heat versus the older ones.
The old radiators with water going through, hot water.
Sorry?
They're you know, the old radiators where they put the water through. That's the kind of heating they're using. It's hot water.
Oh.
Yeah.
The new ones?
Yeah, the new ones, yeah.
Okay. And would there be, the reason I'm asking that is, would there be current buildings downtown close to the rail yards that are radiant that you would know? Does anybody know?
No, there's no buildings.
Traditional heating. Radiant heating is the in-slab heating.
Yeah.
It's become more popular currently because it's more efficient in the long run. It costs a bit more to install, but it reduces capital costs in the long run.
There's more radiant heating in Kistic Tower than Norwood City combined.
Really? That's interesting. Yeah, I mean, it's a great building if you ever get a chance to go through. And they're allowed to open their windows and everything. It's great. Yeah.
All right, are there any other questions?
But just a comment with respect to the area, the potential redevelopment area, as a greenfield project, as a brand new project, where a district heating project was incorporated into whatever is going to be built there, would just be suited so well to a geothermal heat source as well.
Yeah, that'd be great.
Well, and you know, this all gets me thinking about the fact that, you know, there are calls for investments by our governments in projects like this. I can see so many boxes checked, you know, retraining the existing drill teams that currently drill for hydrocarbons, you know, the steel plant. I mean, this seems like a project that's just ripe for that kind of green investment. And so I guess I would just say let's thank you very much for your efforts in championing this and for telling us about it today. It's been extremely informative. So with that, if there are no other questions.